So our next speaker is the winner of the Patricia Tompkins Thesis Prize. And this is a prize given for people working in instrumentation science relevant to astronomy. And we should all remember that all these lovely results we see are the result of somebody building a superb instrument somewhere, and we must thank them very carefully and sincerely for all the work they do. So our Patricia Tompkins Thesis Prize winner is Dr. David Cuadrado from the UKRI Rutherford Appleton Laboratory, who's going to talk about millimetre-wave low-noise amplifiers for the ALMA telescope. David.
Okay, so thank you very much for the introduction and good afternoon, everybody. Well, today is a day of great happiness for me. I am truly honored that the Royal Astronomical Society has selected me for the Patricia Tompkins Thesis Prize. So I would like to start my presentation by thanking both this institution and also the Patricia Tompkins Foundation for the prize and also for offering me the opportunity to present my work here today. So I won this award for my University of Manchester PhD thesis, which is titled Millimetre-Wave Low Noise Amplifiers for the ALMA telescope. And hence, this is the work that I will present here today. To give you a little bit of background, this project falls within an international collaboration led by the European Southern Observatory, which is working on the development of a receiver prototype for ALMA band 2+3. This is a combination of two individual bands of the telescope, 2 and 3, into a single receiver instrument. And during my PhD, I worked on developing the first low-noise amplifiers for this project. So I completed my PhD in June 2017, and right away after this, I started working as a researcher, as a postdoctoral researcher at the University of Manchester. My postdoc was a continuation of my PhD project. I was still working on improving the performance of the ALMA band 2+3 LNAs. So I will also talk about my postdoctoral work later on during the presentation. And just to complete my introduction to you, at present I am working, as the chairman said, as a radio frequency engineer at the Rutherford Appleton laboratory. So in this slide, you can see the table of contents that I will follow throughout this presentation. I will start explaining the characteristics of the ALMA telescope and the specifications of the new band 2+3. And then I will show the work that I did during my PhD. I will start showing the design of my best MMIC. MMIC stands for Monolithic Microwave Integrated Circuit, and these are very small microwave circuits fabricated with highly advanced semiconductor technology that perform the signal amplification. Then I will show the characterization results of the MMICs. And I will show how the best ones were selected for packaging into highly integrated modules with waveguide connectors that I also designed as part of my PhD. And lastly, to conclude this section, I will show the characterization results of the fully assembled LNAs. Then I will show, as I said before, the work of my postdoctoral, the work that I did during my postdoc, which was a continuation of my PhD. And then I will show the current state of the ALMA band 2+3 receiver prototype that is being developed by ESO and the band 2+3 consortium. And lastly, I will finish the presentation setting some conclusions about this work. So as I am sure most of you are aware, ALMA is the largest millimeter and submillimeter wave telescope currently in existence. It is an interferometric array located in the Chilean desert of Atacama at an elevation of 5,000 meters, and it is being developed by an international partnership between Europe, represented by ESO, North America, represented by NRAO, and East Asia, represented by NAOJ, in cooperation with the Republic of Chile. The telescope itself consists of 66 high-precision antennas. 50 of these antennas have a diameter at each of 12 meters and operate together as a unified science machine performing observations with very high angular resolution. The maximum baseline of this array can vary between 150 meters and 16 kilometers. And in its most extended configuration, it can achieve an angular resolution as high as 0.04 arcoseconds at 100 gigahertz. And then the telescope also has what is known as the Atacama Compact Array, which has, on the one hand, 4 12-meter antennas, which are used individually to measure properties that cannot be measured with interferometry, and also 12 7-meter antennas, which are used as a smaller interferometer with lower angular resolution than the main array. Apart from the interferometer and the large dishes, the other crucial element for the detection of the astronomical signal is the front end. And in this sense, the ALMA front end is far superior to any other existing system. It is prepared for receiving signals in 10 different frequency bands that range from 31 gigahertz to 950 gigahertz. And here, if you look at this table, you can see the specifications for each band in terms of frequency, maximum receiver noise over 80% of the bandwidth, and maximum receiver noise at any RF frequency. So in particular, for this project, I was interested in bands 2 and 3. Band 2 ranges from 67 gigahertz to 90 gigahertz. The maximum receiver noise over 80% of the bandwidth is 30 Kelvin, and at any RF frequency is 47 Kelvin. And the ALMA band 3 receiver cartridge will operate from 84 gigahertz to 116 gigahertz with a maximum receiver noise temperature over 80% of the bandwidth of 37 Kelvin, and the maximum at any RF frequency would be 60 Kelvin. It is important to mention at this point that the band 3 receiver is already installed in the telescope. It is fully operational, and it was developed with SIS mixer technology, whereas the band 2 receiver has not been developed yet, and it is in the still unoccupied slot for ALMA band 2 where we would like to put a band 2+3 receiver. In this picture, you can see on the left, you can see a photograph of one of the ALMA front ends, which was developed at RAL, at the Rutherford Appleton laboratory. It basically consists of a very large cryostat, which has 10 slots for allocating each of the receiver cartridges that I showed before in the previous table. And at the right, you can see a picture of one of the ALMA receivers. In this case, it's for band 3, and it was developed in Canada. So before we proceed any further, I would like to show the structure of a typical LNA-based receiver, so that those of you who are not familiar with it can see where the LNA fits and also understand the importance of this component in the receiver chain. So the incoming signal from the telescope is directed through a network of optical components to the input of the receiver, to the feed horn at the input of the receiver. And then the signal is amplified, typically by a factor of 1,000, by the low noise amplifier. The output is then frequency down converted to an intermediate frequency range by a mixer and local oscillator combination. And then in the intermediate frequency range, further amplification and filtering occurs to prepare the signal for its final detection and processing. And at the bottom of the slide, you can see the equation that gives you the noise temperature of an LNA-based receiver like the one that I am showing at the top. So this noise temperature of the receiver would be approximately equal to the noise temperature of the LNA plus the noise temperature of the mixer divided by the gain of the LNA plus the noise temperature of the subsequent IF components divided by the gain of the LNA multiplied by the gain of the mixer. So you can see that this equation is totally dominated by the performance of the LNA. If we have an LNA with low noise temperature and high gain, then the noise temperature of the receiver will be very low. So what is the purpose of this research work? As I said before, there is an international consortium led by the European Southern Observatory, which is working on the development of a band 2+3 receiver prototype for ALMA. And me and my group were doing the low noise amplifiers, for this prototype receiver. Once the final band 2+3 receiver prototype has been finished, and depending on its final performance, the ALMA board will decide if this new band is incorporated into the telescope or not. The advantages of incorporating this band into the telescope would be, first of all, a cartridge would be free for allocating a new receiver cartridge for a new frequency band. And this would increase the telescope's observational capacity. Secondly, this new instrument would allow for the simultaneous observation of spectral lines across a wider frequency range, and thereby it would enhance the science that astronomers can do with the telescope. And lastly, it would provide operational advantage. This new receiver would use LNA technology, as I said before, which achieves excellent performance when operating at 15 Kelvin ambient temperature, whereas the existing band 3 receiver uses SIS mixer technology, which can only operate at 4 Kelvin or less in order to function properly. As I said before, ALMA is the most advanced millimeter and submillimeter wave telescope in the world, and this means that the specifications for each receiver band are already very high. As you can imagine, if we want to combine two of these bands into a single instrument, the specifications become much higher and much more difficult to meet. So they can only be met by using state-of-the-art technology. And for designing the mimics for this project, we used the 35 nanometer indium phosphide process of Northrop Grumman Corporation, which is an American foundry to which we have access thanks to a fantastic collaboration with Caltech and JPL. I have explained the background to the project, and before I start explaining the technical details of the amplifiers, I would like to acknowledge the contribution of some people who have helped me and supported me a lot during my PhD. So this would be my my PhD supervisors and postdoctoral line managers, Professor Daniel George and Professor Gary Fuller, to whom I am also very grateful for nominating me for this prize, and my collaborators from Caltech and JPL, where I spent 6 months working as a visiting PhD researcher. But there are also a number of other groups and people who have contributed to the development of the Band 2+3 receiver prototype. And this would be my colleagues from ISO, who are actually leading the project, my colleagues from RAL, INAF, NAOJ, the University of Chile, Chalmers, Jeves, etc. There are many institutions. So thank you very much to all of them for their great work on this project. And now I am going to explain the work that I did during my PhD. As I said before, the low noise amplifiers that I developed were developed with MMIC technology. MMIC stands for Monolithic Microwave Integrated Circuit, as I said before. And the MMICs are basically the core of the low noise amplifier. They are the chip that perform the signal amplification function. During my PhD, I developed 4 different MMICs for ALMA. 2 of them were for ALMA Band 2+3, and 2 of them were for ALMA Band 2. And to develop them, as I said before, I used the 35 nanometer indium phosphide process of Northrop Grumman Corporation. Here at the bottom of the slide, you can see a picture of one of the ALMA Band 2+3 MMICs that I developed. This is actually a fabricated device. And it's the one that provided the best performance. So it's the one that I will talk about throughout the rest of the presentation. This is a design, a MMIC design with 2 transistor stages. So here you can see the first transistor, second transistor, and their corresponding matching networks to provide minimum noise temperature and maximum gain. Here you can see the RF input, and here you can see the RF output. And these are the DC pads for biasing the transistors. So there is the gate and the drain of the first transistor, the gate of the second transistor, the drain of the second transistor, and then a ground pad. It is interesting to notice that the size of the chip, it's a magnified picture, but the size of the chip is actually very small. It's approximately 1 millimeter square. And this is one of the reasons why we need to integrate these MMICs into highly integrated modules with waveguide connectors. Once the fabrication of the chips had been completed, and given the relatively high chip-to-chip performance variability between MMICs fabricated within the same wafer run, it is necessary to screen the samples with a non-destructive cryogenic probing process that allows the best ones to be identified. For this reason, I tested most of the available chips at the cryogenic probe station at Caltech's Cahill Ray Astronomy Laboratory. I tested the chips at an ambient temperature of 20 Kelvin using the Y-factor method equation. So this method for characterizing the noise temperature of the devices basically consists of integrating the device under test in an heterodyne receiver, like the one that I am showing here, and presenting at its input a variable temperature load, which in this case changed temperatures between 32 Kelvin, that's cold, and 45 Kelvin, which is hot. And then by measuring the total power in the intermediate frequency range, you can apply the equation that I am showing here and calculate the noise temperature of the receiver. If you do this 2 times, one with the device under test and one without the device under test, you can know what's the actual contribution of the device under test. Here you can see a picture of the cryogenic probe station at Caltech. And on the right, there is another picture that I took while I was probing one of my MMICs, probing testing. So in this case, you can see that there is an RF probe for the input of the MMIC, an RF probe for the output of the MMIC, and then another probe to provide the necessary DC signals to bias the transistors. If you want to know more about this instrument, this would be a good reference. And here are the results that I obtained for a set of MMICs as tested in the cryogenic probe station. This instrument basically gives you information about the noise temperature and the gain of the devices. However, the noise temperature measurement is not an absolute noise temperature measurement. It's a relative noise temperature measurement. It allows you to compare MMICs within the same measurement. It's not an absolute noise temperature measurement because the noise contribution of the lossy input probe has not been calibrated out. But from this table, you can select which MMICs are the best ones. So for instance, each of these traces corresponds to a different MMIC. This is for the noise, and this is for the gain. So here, noise-wise, you can see that the MMIC represented in black is much better than the MMIC represented in blue, for instance. So the next part of the work consisted of, once the best chips had been identified with the tests on the cryogenic probe station, selecting them for packaging into highly integrated modules like this one. So I also designed the highly integrated modules as part of my PhD work. And the design of the highly integrated module included not only the design of the LNA housing, but also the design of a waveguide to microstrip transition and an off-chip protection circuit to protect the MMIC against improper biasing and RFI. You can see that the amplifier is equipped with a micro D connector with 9 pins here to provide the MMIC with the necessary DC signals, and a waveguide port here for the RF signals. This is the RF interface. And there would be another one. This is the input. The output would be on the other side of the block. In order to couple the electromagnetic fields propagating along the waveguide channels into the microstrip lines at the input and output of the MMIC, it is necessary to use a waveguide to microstrip transition. As part of this work, I also designed my waveguide to microstrip transitions using quartz, a material with low dielectric constant and that has the great advantage of being transparent, and so allows for an easy removal of the excess epoxy during the assembly process. Here on the left, you can see a picture of the electromagnetic model that I used to simulate and to design the waveguide to microstrip transitions in a 3D simulator called HFSS. The advantage of this software is that the advantage of this model, an interesting feature of it, is that it accounts for. I included the bond wire to account for its performance during the design of the waveguide to microstrip transition, and this way I could compensate for its inductive performance during the design of the probe. Here you can see the simulation of this model. So according to this simulation, the probe, the transition, would have an insertion loss less than 0.25 dB across all of the operating bandwidth. And the matching, considering a 50 ohm system, would be better than 15 dB. And here you can see a picture of one of the fabricated waveguide to microstrip transitions. This is obviously a magnified picture. The off-chip protection circuit is necessary to protect the MMIC against improper biasing and RFI, as I said before. The off-chip protection circuit that I included in my amplifiers consisted of a 15 picofarad shunt capacitor next to the MMIC that provides low impedance at frequencies higher than 1 gigahertz, and then a PCB which has 100 nanofarad shunt capacitors in both drain and gate lines that provide low impedance at frequencies higher than 160 megahertz, and also in the gates I included a 10 ohm resistor that, together with the 15 picofarad resistor, operates as a low-pass filter, providing additional attenuation above the cutoff frequency of 1 gigahertz. And here is a picture of the interior of one of the fully assembled low-noise amplifiers. So you can see that the MMIC is here, the waveguide to microstrip transitions are here, and this is the off-chip protection circuit, including the bondable capacitors. So the way this works is the RF signal would come into the LNA through this waveguide channel, then it would be transformed into microstrip format through the waveguide to microstrip transition, then it would be amplified on the MMIC, and then at the output it would be converted again to waveguide format and propagated out through the RF output waveguide channel. The fabrication of the blocks was performed both at the mechanical workshop of the Rutherford Appleton laboratory and the University of Manchester. And the assembly of the MMICs was performed by a senior technician from JPL. Her name is Mary Soria. So once the machining of the LNA housings had been completed and the blocks had been fully assembled, the next step of the work consisted obviously of characterizing them. I characterized the amplifiers both at room temperature and cryogenic ambient temperature of 20 Kelvin. At room temperature, I measured the S parameters, the noise temperature, and the 1 dB compression point. And at cryogenic ambient temperature, I measured the noise temperature and the gain. However, due to the time limitation of this presentation, I will only show the noise temperature characterization at cryogenic ambient temperature, which I did using the setup that you can see here. So this is basically, this test setup is embedded on a 20 Kelvin cryostat and contains two chains for characterizing two amplifiers in each cool down. So the mechanism is also very similar to the one that I described before, and it consists of applying the Y factor method. So you have a variable temperature load here, which in this case changes temperatures between 25 and 75 Kelvin, and then you have your amplifier under test, and a second amplifier to reduce the noise temperature contribution of the subsequent elements in the receiver chain. Additionally, I also included a cryogenic isolator, which is here and here, to improve the matching between the amplifier under test and the backend amplifier. And this is probably the most important graph that I produced during my PhD. So it shows the noise temperature of 5 LNAs for ALMA band 2+3, and each of these traces would be one of the amplifiers. And you can see that there are 3 amplifiers here which have noise temperature less than 28 Kelvin from 67 gigahertz to 116 gigahertz. Sorry, from 70 gigahertz to 110 gigahertz. So at the time of producing these results, these were the best amplifiers ever reported in the literature in this frequency range. And in fact, today there is still nothing better. There are some similar things, but nothing better. So now, as I said before, I'm going to explain briefly the work that I did during my postdoc to try to improve the performance of the amplifiers for ALMA Band 2+3. So basically, I pursued 3 lines of work. The first line of work consisted of producing new MMIC designs with improved performance. I produced 3 new MMIC designs. The common characteristic of all of them is that there is a performance improvement in the band 2 range. So here the dotted line is the simulated performance of the MMICs from the previous generation, and the solid line is the new generation. So I improved the performance in the band 2 range by approximately 2 Kelvin. And also, 2 of the new designs have an additional transistor stage to increase the gain of the MMICs and hence the amplifiers. Additionally, the last MMIC design has a larger device at the output to also improve the 1 dB compression point. Unfortunately, these MMICs have recently been fabricated, and I cannot show their measured performance yet. But the 2 other lines that I pursued for improving the performance of the amplifiers was, first of all, improving the machining quality of the LNA housings. In the graph that I showed before, there are devices which have an LNA housing that has been machined at RAL, like this one, and in other devices that have an LNA housing that have been machined at the mechanical workshop of the University of Manchester, which with the microscope looks like this one. So you can see that the machining quality of the LNAs machined at RAL is significantly better than those machined at Manchester. The interesting thing is that if we go back to this graph, the only block that has been machined in Manchester at RAL is this one, the one that shows a much better performance at the high end of the operating bandwidth. The other ones start rolling up at frequencies above 110 gigahertz. So by improving the machining quality, I hoped the performance of the amplifiers would improve in the high end of the band. And the third line of work that I pursued during my postdoc to improve the performance of the amplifiers consisted of designing a new waveguide to microstrip transition. The waveguide to microstrip transition cannot be tested alone. It's really difficult because of the interfaces that it would need to be tested. So a way of testing it is embedding it in a circuit like this one, just with a through line in the middle, not using a MMIC. So I did that using the waveguide to microstrip transition from the previous generation and the new one. The new one shows the performance here displayed in green. And you can see that the losses are better than 1 dB across all of the frequency range of operation. Whereas the previous design rolled down a little bit at low frequencies and also massively at high frequencies. This is still good, but we are trying to achieve state-of-the-art performance, so if it can be improved, it needs to be improved. So when you put all these things together, well, not the MMICs, because as I said before, they have just been delivered to us. When you put the new LNA housings machined with the best quality and the new waveguide to microstrip transitions in an LNA and you test them, in this case, I didn't test the blocks individually. I cascaded 2 amplifiers to provide the gain that needs to be provided for the receiver, which, as I said before, is approximately 1,000 level of amplification. So you can see that the performance of the new block is displayed here in red. This is the noise temperature, and it has an average noise temperature of 26.3 Kelvin across all of the operating bandwidth, whereas the previous one had an average noise temperature of 27.5 Kelvin. So there is an improvement. And this improvement is particularly noticeable in the high end of the band. The ripple here in the gain of the on the second generation of amplifiers is due to the fact that we didn't have a cryogenic isolator available to put between the 2 amplifiers when we were doing the tests. So yeah, that means that we are working in the right direction and the performance is improving as expected. And just to conclude, I would like to show what is the current state of the band 2+3 receiver, based on the tests that had been done by the European Southern Observatory and INAF. So we have so far built 2 versions of the ALMA Band 2+3 receiver. The first version was built and tested in October 2017, and it had an average noise temperature of 42.8 Kelvin across all of the band 2+3 frequency range. And the new results that we got in July for the new version of the receiver have an average noise temperature of 36.9 Kelvin, which is quite remarkable in my opinion. So we are fully compliant with the specifications of ALMA Band 3, and we don't meet yet the specifications for ALMA Band 2, but we are getting very close to it. So I am sure with some improvements in the near future, we will manage to be there. So the conclusions of these presentations is that there is a Band 2+3 consortium working on the development of a Band 2+3 receiver, which would be very beneficial to the astronomical community because it would increase the telescope's observational capacity. It would enhance the science that astronomers can do with ALMA because they could observe more spectral lines simultaneously. And also, it would provide operational advantage by reducing the cooling requirement from 4 Kelvin as required by the current Band 3 receiver to 15 Kelvin as required by LNA technology. During my PhD, I built the first low noise amplifiers for this project, and the best ones show noise temperature less than 28 Kelvin from 70 gigahertz to 110 gigahertz. And the current state of the ALMA Band 2+3 receiver prototype is that it has an average noise temperature of 36.9 Kelvin across all of the operating bandwidth from 67 gigahertz to 116 gigahertz. So thank you very much for your attention.
So questions for David? Yes, Lindsay.
This is wonderful work. Congratulations.
Thank you.
Is there one property in particular of the MIMIC that makes it a record-breaking device for the noise temperature?
Well, it's the process that I am using. It's quite novel. It has transistors with very short gate lengths, and this is really good towards getting devices with very good noise temperature. So yeah, I am using the best possible technology. Then, if your question is more related to the way I design the mimics, I don't really know. I mean, some people have asked me, why did you get so good results? And I honestly don't, I don't think I have like a key and ingredient that I can say it's because of this. I think it's just doing the design very carefully and I don't know, getting, I got support also from several people who, I don't know, yeah, it's really difficult to give you like the key ingredient of the recipe. Because
Other questions? Yes, Quentin.
Obviously, with the small batches you showed there's a variation in the noise coming with them. Obviously, you're going to be making many more of these. Do you see the process getting so that the noise variation is reduced, or will you have to characterize each one very carefully?
You have to characterize each one carefully. So, well, every time there is a wafer run, we learn stuff from it. So this is a non-commercial process. It's a process that doesn't provide you with a design library. You have basically to design everything, to draw everything manually. The simulations that you do not always fully match the measurements afterwards. So you need to learn about the process. And yeah, for every wafer run that we participate in, we keep learning about it and we can apply the new knowledge that we get. But still, in each wafer run, there is a high chip-to-chip performance variability. So we get lots of mimics in each wafer, but they don't have exactly the same performance. There is always a standard deviation in the noise temperature performance and also in the gain. So you need to fabricate multiple chips in order to get some good ones, let's say.
So it sounds like you're getting a spin-off, which is additional for the ALMA LNAs you're producing, so we get an extra benefit from this work, which is excellent.
Yeah, thank you.
Okay, David, thank you very much indeed.
Thank you.
Just to focus everybody's attention, that talk was about objects that were 1 millimetre by 1 millimetre in size. I find that absolutely extraordinary.